Hi class, in this lesson we're going to be working with 3D solids that are created using revolutions. The objective for this lesson will be to be able to construct a 3D solid using revolution and to be able to find a volume of solid using the disk method. In the last lesson of 3D solid that we look at, we use cross sections to create these 3D solids. In this lesson, we're going to look at another type of volume questions, which comes from rotating a bounded area around a line. Okay, so this is actually the more common type of problem that you will see in volume problems. Since anytime we rotate a region around a line, it creates a circular cross-section. Our formula for the area will be based on our pi r squared, the area of a circle. There are two types of cross-section that can occur when we're rotating these regions about a line. Okay, the first kind is called the disks, and they're just circles. Okay, and the other one is called the washers, and washers are also circles, but they have a circular cutout in the middle of it. For this video, we're going to be focusing on the first method. We're going to be finding the solid of Okay, so a disk will be a full circle. So to find the area, we will take the radius and we'll square the radius and then multiply by pi. So area equals to pi r squared. The first method of finding the volume of solid of revolution is using disk to integrate different area of disk. The cross-sectional area will be a disk when there's no empty space between the bounded area and the axis of revolution. So if we have this function here and this is our area, we can see that if we're rotating about the x-axis, there is no space in between. So when we rotate it, we're creating circular cross sections. Okay, so here is our function, and I want you to imagine that we are attaching this function to our x-axis. This is our axis of rotation, this axis of rotation by these two vertical lines, which is our lower and upper limit. Okay, so we're going to find this solid by rotating this function around, okay, all the way around the x-axis. So this is what's going to happen. As you rotate this function, okay, we're going to rotate the function around the x-axis. See how it goes all the way around? Okay, let's see that. Okay, let's do that again. I'm going to turn the paper a little bit so we can see that rotation a little bit better. Okay, here, I'm going to rotate our function around the x-axis. And as you can see, as it rotates it, the cross-section right here is actually a circle. Okay, and this circle is what we call a disk because there's no empty space. It's a full circle. Okay, so and this disk has a radius from our center of rotation to the function. Okay, so think about how this is represented by x. Okay, all right, so as we move this disk around, right, along our interval, you can see that the size changes because the radius changes, because the distance between the center of rotation and the function changes, right? And this area of these disks is what we're going to integrate to find the volume of the solid. Okay, so let's do that again. Now this time we're going to look at the actual solid. So let's go ahead and rotate that again, and as you can see, as you rotate it, it forms a solid, right? And the cross section are circles that we will integrate, circles whose area we're going to integrate to find the volume. Okay, so as you're looking at these circles, I want you to think about how can we represent the area in terms of x, in terms of that function. Okay, to derive the formula, we have to consider the cross-section because we're going to integrate the area of the cross-section. And since we're rotating, we're creating these circular cross-sections, we're going to use pi r squared. Okay, and what is the r in terms of x? Well, the r in terms of x is actually f of x because it goes from the x-axis to where the value of f of x is, right? So let's plug that in. Okay, so we're going to integrate with respect to x because, again, when we're rotating about the x-axis, we're creating these cross-sections that are perpendicular to our x-axis. Therefore, we are going to integrate with respect to x. Okay, so if we plug in the values, we have our formula. The volume can be found by pi times the integral from a to b of f of x squared dx. Now let's find the volume of the solid created by rotating around the x-axis, the function of square root of x, y equals to 0, and x equals to 4. So let's go ahead and pull up the graph of the function. We know that the domain, it will be x greater or equals to 0, so it's only positive numbers, 0 or greater. Okay, so we know our lower bound is 0, and we were given a upper bound of x equals to 4. Okay, we can also do it algebraically by setting these two equals to each other, the two y's equal to each other, and solve for x. Right, so we know that the interval will be between 0 and 4. So that's going to be the value for a and b. Okay. Now this is our radius. The radius goes from the x-axis to the function, and we're going to rotate it this way. So to sketch these, usually I would put a little tick mark right here and right here, 2 up, therefore 2 down. They're kind of symmetrical, and then I sketch out the solid. Okay, so let's go ahead and pull out the formula. We know that our radius is represented by f of x, so go ahead and pass in f of x into our formula. Okay, simplify, integrate, and evaluate. Okay, the volume of the solid equals to a pi. And here is our beautifully rendered 3D solid. So when we were working with area and we're using the definite integral to find area, we were able to choose whichever variable we think is easier to integrate with. You know, we don't have to cut in pieces, but this does not apply when we're working with solid of revolution. And that's because when you rotate that region about different axes, you actually get a different solid. So let's take a look at this same shape. This is the area under y equals square root of x between 0 and 4. So let's lay it down a little bit to see. Let me move it up a little bit. Okay. Okay, so if we were to rotate that region about x-axis, or our x-axis is our axle, so let's go ahead and rotate that. We get this shape right here. But if we do that, we take that same region, but this time we're going to go this way. We're going to rotate about the y-axis, so making this green one our axle. Okay, we are going to get a complete different solid. So if we were to integrate the same region with respect to different variable, we're actually going to get different answers because we're finding the volume of a different solid. If we're asked to rotate around a vertical line, then when we create this solid, we'll be creating horizontal discs. In other words, these cross-sections that we create will be perpendicular to the y-axis, right? So we will have to integrate vertically per se. So our integral has to be built in an interval that is between y values. Okay, so because we are integrating vertically, we are going to be integrating with respect to y. So the process of integrating with respect to y is very similar, except for since we created these horizontal discs, our r is going to be a horizontal segment instead of a vertical one. Okay, so and this r is the difference in x values, so we're going to rewrite our equation in terms of y, which we're going to rewrite it as x equals form. And this just means we're going to solve for x. Okay, so once we have that, then we express our r in terms of y. It's r equals to f of y, and we can integrate with respect to y. And here is our area in terms of y is pi times f of y squared, and we're going to integrate vertically, right, dy. So we're going to go from c to d. Okay, so let's go ahead and plug in the values, and I can factor out the pi because pi is a constant, and here we have our formula for integrating with respect to y. Okay, now let's use that same function, but this time we're going to rotate it around the y-axis, and we're going to consider the interval from 0 to 2, y equals to 0 and y equals to 2. Okay, so here is our graph. I'm going to go ahead and draw my radius, and I'm going to draw a tick mark right here where radius hits the function. And of course, I'm going to reflect that point across my y-axis, so basically symmetrical right here. Okay, and then I will draw the rotation and draw the mirror image of my function. Okay, reflect, and this is a sketch of our solid. So for every single problem, you need to start with a sketch of your solid. Okay, now the first step to do is to rewrite our function in terms of y. So that means we're going to solve for x. Okay, so we're going to isolate x. Okay, so f of y, which in this case, x is f of y, because we're expressing the same function in terms of y this time, okay, equals to y squared. So we're going to use that as our radius. We're going to plug it into our volume formula, simplify, and we're going to integrate, evaluate. We're going to get 32 over 5, which is approximately 6.4. Next, we're going to do the same thing, but this time, instead of rotating it around the x-axis, we're going to rotate it around a line that is parallel to the x-axis. We're going to rotate it around the line y equals 3. So we'll start by graphing the function, which is right here, y equals to square root of x. Okay, and the regions is enclosed by y equals to square root of x, y equals to 3, and x equals to 0. So this is our region. And we're going to be rotating around the line y equals to 3. Okay, so again, let's see. What is our radius now? Okay, so this is our radius here. It goes from the axle of rotation, and it goes the other way. So this is how we rotate it. Okay, let's sketch the reflection. And now we have the sketch of the solid. Okay, so here is our formula for the volume, and we have to identify the radius. What is the radius here? The radius goes from the axle of rotation to the function, right? So it goes from 3 minus the function. So our radius is 3 minus our function, which is 3 minus square root of x. Okay, and we have to identify the lower and the upper bound, and we're given the lower bound of x equals to 0. Okay, and right here is our upper bound, and the upper bound is where our function and the axle, the line of rotation, intersect. So let's go ahead and set them to equal. Okay, and we can see that when x equals to 9, these two functions intersect. Okay, so let's go ahead and plug them in. These values, we have our lower bound of 0 and upper bound of 9, and here is our radius. Again, we factor out the pi because pi is a constant. Okay, and the easiest way, in my opinion, to integrate this is to distribute it, to multiply it out, and then use power rule. Okay, once I integrate, I'm going to evaluate, and it is about 13.5 pi. Now let's do the same thing, but this time we're going to rotate our region around a vertical line, x equals to 4. Now x equals to 4 is parallel to y-axis, which means our cross-sections are going to be perpendicular to our y-axis, which means we're going to integrate with respect to y. Okay, so we'll start by graphing the function, and again, we're going to identify the region. The region is between square root of x, y equals to 0, and x equals to 4. So this is our region. Okay, now this is our axles of rotation. Okay, we're going to rotate it this way, and here is our radius. The radius goes from the axle to the function. Okay, so it's the difference between the axle and the function. Okay, so let's go ahead and flip it the other way. So we have our radius. Okay, and we're going to rotate it this way. Okay, and then we're going to sketch the reflection of our function. Now we have our 3D solid sketched. Okay, now look, our radius is going to be horizontal. segment stacked in y, right? So it's going to be the difference between the axle and the x value of our function. So we have to rewrite our function in terms of y. We have to know what x value is, so we're going to define it in terms of y. So we're going to solve for x. Take our function and solve for x. So x equals to y squared, or our f of y equals to y squared. Okay. Next, we have to define our radius as f of y, which means our radius is 4 minus y squared. Okay, the only thing left to do is to figure out what our interval of integration is. It's going to go from 0 to 2 based on our graph, but if we want to find it algebraically, we will set x equals to y squared and figure out when they're equal. So we know that x equals to 4, right? This is where we're going to stop. X equals to 4. So y squared equals to 4 when y equals to 2. So here is our interval, 0 to 2. Okay, let's go ahead and plug these information into our formula. Again, with these type of integrals where we have just a binomial squared, it is easiest to multiply it out. Again, this is our radius squared. Okay, we're going to integrate, evaluate our integral, and it reduces to, it rounds to about 17.667.